No, it's not that long. Not that bad. All right, so remember our loop rule? We did those guidelines. Let me just go back and remind you of them. When we go across a resistor, with the current, we get a negative change in potential. And we go across a resistor against the current, we get a positive change in potential. If we go across a battery from big to small, we get a negative change in potential. Remember the slide? Whee! And then if you go from low to high, you get a positive change in potential. So you'll need those guidelines to help you apply the loop rule. And let's try that here. What happened, Mike? Sorry, let me restart this. I don't know what happened. All right, so what is the current in this circuit? First, you want to pick a direction for the current. You know, later when I work this, I'm going to pick a direction. I don't know. Sorry, I'm going to pick a direction like that. But it doesn't really matter what direction you pick. All right, I'm just picking a random direction. So pick a direction for the current, and then pick a direction to go through the circuit. So I might choose to go in that direction through the circuit. You can choose what you like. Write the loop rule for that, and then solve for the current. So go through and ask yourself, what is the change in potential on each element, each resistor or battery? There. All right, let's try to wrap this up soon, folks. We're confused and lost. Is that what you said? Yeah, okay.
See, if I put my batteries on, I click it like that, it won't work. That's,
Oh, right.
Both positives,
Right, that doesn't work, right. All right. All right, let's just a few more seconds, okay? So just, if you don't know, just guess, okay? I'll stop at 4:10. Trust me, once you see it, this isn't that difficult. It's just you sort of have to do it. I think the answer is A. I'm not positive. I might go back and change that. Let's see. So, confused, lost, and not positive. All right, so I'm going to move in this direction. So I'll just write the loop rule. So I have negative IR right across this resistor because I'm going with the current. So that's just negative I times 1 minus 6.6I plus 18 because I go up in potential minus 2I and then minus 12 because I go down in potential. And that's equal to 0. And then I just solve that equation for I. So I get, what's that? Minus 9.6I plus 6 equals 0. And then I is negative 6 over negative 9.6, which must be 0.63 amps. All right. Don't worry, we'll do this much more times.
So, can you go over that one more time for us?
Yeah, writing the equation, that's the hard part, right? So I just picked a direction for the current. I chose it to be in this direction. Andrew?
Where does thing came from, this equation?
What?
Where did this equation come from?
Oh, that's what I'm doing right there. I'm going to show you.
But that's when we figure this out there in the equation. Well, the equation's part of the...
The equation is just an application of the loop rule. It just says that the sum of the potentials across any loop equals 0. And so I was just summing up the potentials around this loop. All right? So I start here and go in this direction. The potential across this is negative IR. That's negative I times 1.
Why is it negative?
Because I'm going with the current, and you got to return to those guidelines. There's really no good answer to why, but when you go with the current, you get a negative change in potential. That's sort of what resistors do. They cause a drop in energy, and so when you go with the current, it's like they're doing what they're supposed to.
You know you're going with the current because
I just chose a direction.
That's the direction that you chose.
Yeah.
If you had just chose the other way, it would have been.
I'll show you what happens when I choose the other way. All right. So across this one, I get negative 6.6I because I'm going with the current. Here I get a change in potential of plus 18. I know that it's positive because I'm going from the little side to the big side, from low to high potential, and so my charges are gaining energy here. They're going up in energy. The I is the unknown, right? I is the current, yeah. And so
you just find the current by going from your volts going across your thing to find your amps, because you know your volts going that way.
you could do that in this case. You're saying that I know that my
Now you got 12 volts across the one ohm, you're going to have 12 amps
no,
to find out.
because both batteries are driving the current. It's not just the 12, not just the 18.
So I is that's the part of it.
Right. In fact, what is, if I were to replace these two batteries with a single battery, what would be the voltage of that battery? It would be 6 volts. And in fact, it would be a 6 volt that would look like this. All right. Yeah. Jose?
Yeah, that's getting me a little confused because he says here on the, what is that, E letter thing?
Uh-huh, the EMF.
Yeah, so you say that when it goes from positive to negative in the battery, E is a negative.
Right.
Then in the other side is a positive. But
Right.
in this case, on the first battery, isn't it like that?
Well, on this one, I go from, this is the negative side to the positive side,
Mm-hmm.
and it goes up. So I get a positive change in potential, and so I recorded a positive change in potential over here. So that does follow those guidelines, those rules. Okay? Let me keep on, just think about that for a second. And then I have a change in potential of minus I times R. That's minus R times I, rather, is 2I. And then over here, my electrons, or my charges, lose energy, so I get a negative 12. And I put each of these into the sum of the potentials. That's where all these values came from. and I just set it up equal to 0.
I got it.
You got it okay? All right. And that's all for I. Now, Chris, you asked, what happens if I change the direction? Let me show you. Because it doesn't really matter what direction you choose for the current or what direction you go through the circuit. Let's say that I chose the current to be this direction, and let's say that I go this direction with the current. Or no, let's go the opposite direction. Let's go this direction. All right, so now I'm traveling opposite the current, so I'm going to have plus 1 times I, so that's just plus I, that's this resistor, plus 6.6 I is positive because I'm going against the current. Plus 18, plus 2I, minus 12. That's equal to 0. If I solve this for I get a 9.6I plus 6 equals 0. So I equals 6, negative 6 over 9.6, or negative 0.63. No, it's positive 18. I'm going this direction. Remember, with the batteries, it doesn't matter the direction of the current. All that matters is the direction that you're traveling across the battery. So if I try, 18 was positive before.
No, but the I's, all those are positive now when they were negative last time.
Because I'm going opposite the current.
But you look like you're going the same way.
Yeah.
I'm going the same way, but I chose the current to be the opposite direction.
You have to show it.
Okay.
Yeah, you have to choose your own direction. Everybody goes their own way, all right? But we all get to the same destination.
But it's not the same answer.
But it is the same magnitude, right? I got negative 0.63, and down here I got positive 0.63. And so if you get a negative value, it means that you chose the direction of the current incorrectly. Yeah, so really, the current in this circuit actually goes in this direction with 0.63 amps.
So
Here,
if you chose that direction that you're talking about, but then chose the direct opposite direction to travel, the answer would still be the same.
if I chose the correct direction for the current, so if I chose this direction for the current, but I traveled this direction, yeah, you would still get positive 0.63. If you choose the direction of your current correctly, you get a positive current. If you choose it incorrectly, you get a negative current.
How do you know which way to go? Is it just kind of guess?
Whatever you want to do, it's fine.
So if you get a negative, just take the negative out and just assume that you went the wrong way. With your,
Right.
Just change the direction.
Right.
So our answers are always going to be positive.
No, sometimes it'll be negative. It depends. Yeah, that's fine. Hey guys, I'm sorry, what?
Before you do the correction, you don't know the direction of current. So how do you know the potential to be positive or negative?
Okay, the current, the direction of the current doesn't affect. Oh, I see what you're asking. You assume that you've chosen the current correctly until you get to the very end, right?
That's what it is. You don't know what's the direction of the current, so you don't know, so you cannot make sure what's the.
Yeah, I understand what you're saying, but you assume, like if you choose it this direction, each time you come to an element, you assume that the current is in this direction. And then when you get to the end, if the current comes up negative, you've chosen the direction incorrectly.
But it's negative or positive depends on the battery potential.
That's true, right.
So if you know the direction of current, you don't know the battery. You don't know what if the potential should be positive or negative.
No, I don't think so. I'm not sure I fully understand, but I'm pretty sure that the answer is no. It doesn't matter if you've gotten your current incorrect. When you're writing out your loop rule, you're just going to assume that your current is in the correct direction. Let's work another problem. because I think it'll become more evident when we work through some multi-loop problems. Is that okay? Can we just put your question on hold, thing, and then we'll see if it's resolved later? I think I understand your question. I'm not sure. All right, let's do some more problems, and we'll see. All right. So first, let's just do it analytically. So not putting numbers in. This is a multi-loop circuit. You will have a multi-loop circuit on the next exam, and it'll be just 2 loops like this. Although, in a real circuit, you can have a gazillion loops. You can have all sorts of business with resistors and batteries, and you can have capacitors in it, and more resistors, and just all laid out on this big grid with all sorts of resistors and stuff. But we're just going to do 2 loops, or 3 loops actually, one that looks similar to this. So there's lots of practice problems for you to work through. There's one in the homework. There's one on basically every exam. All right, and then we'll do a couple in class as well. Okay? With these circuits, you can write a system of 4 equations. All right, but you only have 3 unknowns in these. You only have the 3 currents that are unknown. And so you don't really need 4 equations, right? How many equations do you need to solve for 3 unknowns? You just need 3 independent equations. And we can actually come up with 4 independent equations. We can use the loop rule to write 3 equations for 3 distinct loops, and then the junction rule. Now in this circuit, I've already shown you the directions for the currents. I won't give you the directions for the currents later on the test, but here I just labeled them. These aren't necessarily the correct directions for the currents. I've just chosen some directions. So a couple of things you want to note is that I1 here, I1 starts here, runs up through here, and ends right there. I2 starts here and goes there. And then I3 starts here and follows there. Anytime you go to a junction, your current will change from one current to another because it's meeting up with another current and they're forming a new current. Follow that? It's sometimes difficult for students to understand. So I2 only occurs in that middle little segment, and I1 only occurs on that left side, and I3 only on the right side. So 3 stops at the bottom. A current always stops at a junction, and a new current takes over. Okay, so we can use our loop rule to write these 4 equations. Let's see, I'm going to start up here and go in this direction and follow the left loop. Why don't y'all just take a moment and write out the loop rule for this, and then I'll give y'all a little head start and then I'll write it. So write the loop rule. I'm going to start here and go in this direction. Writing the loop rule for the left loop, going through here, up here, and then back to the original point. The first thing you encounter is V1 plus or minus. It's plus V1, right? Because you're going from little to big. R1 plus or minus? Minus. Minus I1 R1. Again, I don't know the direction of this current for sure. I've just chosen a direction. And because I'm going with the current, I take a negative change in potential. How about V2 plus or minus? It's negative V2. Not because I'm opposing the current, but because I'm going from big to little size. So my charges lose energy as they go in this direction. It's like a big slide. And then R2 plus or minus? It's plus I2 R2. And then that's equal to 0. So that's my left loop equation. My right loop, yeah.
The center one from R2, you start from the bottom and went up.
Uh-huh.
You can go I2 starts from the top and goes down.
But I'm following my loop. So I started up here, and I follow the loop down here. I go through V1, I go through R1, make a left or swing up, go through V2, go through R2, and then I come back to my original position.
Your right loop would start.
Right. The choice that you make for the direction of the current is a separate choice than the direction that you travel through the loop. They're not really related to one another. Let's try the right loop. See, I'm going to start. I'm going to start up here, going in this direction as I travel through this circuit. You can just a little bit of a head start.
Does it really matter if you go that direction or the other
It
direction?
doesn't. No, you can go the other direction. It's just I want to. That's how I'm going to write it. If you want to do the same, that's fine. Okay. Plus or minus R2? It's negative. You're going with the current. Yeah, so it's negative I2 R2 plus V2. Because your electrons gain energy, they're going up in energy. Minus what? V3, because I'm going down in energy. And plus I3R3. Very good. Zero.
Question.
Yeah.
Like, before you wrote that equation on the right loop, I started writing it on my own before you did. And so I started and went through R3, then
Okay.
V3 that direction.
You did this?
Yeah, that doesn't matter.
No, let me show you. So if I do this, it's minus I3R3 plus V3. They're going to be the same equation. Let me show you why. Minus V2 plus I2R2. How are these equations different? Right, one is just the negative of another. So I just multiplied this one by -1, I got the same equation. So it doesn't impact anything that you do. Right? It doesn't even make it more difficult to solve in the end. It's going to be exactly the same. So it doesn't matter how you choose it. Now we'll see later, if you have some information, one equation might lead you to an answer more quickly than another equation. I'll show you later, we'll see that. Jose?
Can you just assume that whatever your V is, the IR is just going to be the opposite of
Whatever what?
your V, your potential is that your IR is just going to be the opposite of it. Like you have negative I2R2, and then the V2 is just positive.
No, those are unrelated. So I could switch the polarity of V2 and just have this as the big side and that's the small side, and then your rule would not work anymore. So those are unrelated. Don't worry, we're gonna get some more practice. We'll put some numbers in here. Let's do the big loop. Okay. I'm gonna start here. I'm gonna go in this direction and go through here. But again, you can go a different direction, whatever you like. Just take a few seconds, get a little head start, if you like. All right, first is plus or minus V1? It's plus V1, right? Because my charges gain energy right there. Minus I1 R1. Plus or minus V3? Minus V3. Plus or minus I3 R3? Plus, because I'm going against the current. Again, the current that I've chosen may or may not be correct, doesn't really matter. That's the end, right? And that brings you back to here. So that's equal to 0. So now I have 3 independent equations. You could solve these 3. These 3 would be kind of difficult to solve, just because all of your unknowns have a coefficient. So it's a coefficient that's bigger than 1. So it's easier to use the junction rule as well. So when you're solving one of these multi-loop circuits, you would choose any 2 of these, and then you would write the junction rule as well. And to write the junction rule, you just pick any junction in the circuit. How many junctions are in this circuit? Right, there are 2 junctions. And so I can pick this junction, and I just say the incoming current equals the outgoing current. What are the incoming currents for that junction? The incoming currents. What's that? They are, right. So there are no incoming currents, right? Which doesn't really make any physical sense. But again, you can choose whatever direction you want for the currents. Okay? So there are no incoming currents. 0 equals I1 plus I2 plus I3. Incoming equals outgoing. Down here, by the way, if you chose this junction instead, it's going to be the same. It's just going to be I1 plus I2 plus I3 equals 0. Yeah. It is possible to get a circuit like that where you have all of your currents add up to equal 0. But what would the currents have to be? It is possible to have a circuit like that where this would be true, but what would I1, I2, and I3 have to be? No, they'd have to all be 0 in order to have that. So it's not a very useful circuit, but that is possible to have it. All right?
But this case was disturbance numbers as they're all the
No, in this case, most likely the circuit would be such that one or more of those currents, I1, I2, or I3, would be negative, right? Because it chose the direction incorrectly. I chose it incorrectly. Was that? Right. Let's do one with numbers. So we'll see some problems later, and you'll see some multiple choice where I just give you a series of equations, and I ask you which of these is a proper application of the loop rule or the junction rule. So we'll see that in practice in a little bit, and you'll see that on the test as well. Okay, so here's a circuit. I want to know the current through each resistor. Now you can choose the currents any way that you want, but I'm going to choose them to look like this. I'm going to have I1 right here. So I'll take that to be I1. I'll take I2 to be in this direction. No reason I'm choosing these. And then I3 in this direction. No particular reason. And then I can write 3 equations using the loop and junction rules. So for the upper loop, I'll have this equation. And let's see, I'm going to start right here, and I'll go in this direction, and then I'll follow this circuit along the upper loop, like that. And just write out the junction rule. So that's going to be 6 minus 1I2 plus 4 minus 2I1. 6 minus I2 plus 4 minus 2I1 equals 0. Then we'll do the lower loop. This one is made really easy, the system of equations, because that lower loop doesn't have a resistor. And so when I write the equation for the lower loop, there is no I3 term in it. So it makes it really easy to solve. Let me show you why. I'm going to take the lower loop, and I'll pick it at this point going to the right. So what's my equation going to be? 6 minus 1 times I2, just like we had before. And then what? Plus or minus 2? Minus 2. 0. So I can take that equation and go ahead and solve outright for I2. But recognize that if I had a resistor down here, I wouldn't be able to do that, because then I would have an I3 term in there. I3 times R. But I made this one a little easier by not putting a resistor down there. And you can see a similar simplified circuit on your exam. It makes the solving the system of equations a lot easier. And then you want to pick a junction rule. And this is where we find our I3. So I just pick any junction. I think I chose this junction right here. What are my incoming currents at that junction? All right, I3 and I1 equals my outgoing current, I2. And I want to solve those three equations. I'm going to call this equation 1, this equation 2, and this equation 3. The first step is just to find out what is I2. So I solve equation 2 for I2. And I find that I2 is equal to 4. All right. On the test, you'll need to also specify a direction. So it's 4 amps to the right. I know that because it's positive here, and I chose it to the right, and so that was the correct direction. I chose the junction rule right here. So my incoming currents were the I1 and I3, and then the outgoing current was I2 right there. But you could choose the other junction. You would just get I2 equals I1 plus I3. All right, now that you know I2, you can solve equation 1 for I1. So that's going to be I1, I'm solving this equation up here, equals negative 6 minus I2 plus 4 divided by negative 2. Did I do that correctly? 6 minus I2 plus 4 divided by negative 2. Yeah, that's correct. Oh, I was just, I took this whole thing and took it over to this side, and so I just negated it. I could have put negative 6 plus I2 minus 4, and then I divided by negative 2. All right, and then I know I2, so this is just a negative of 6 minus 4 plus 4. That's 6 over negative 2, so that's 3 amps. That's right. And 3 amps for I1. Since I chose the direction counterclockwise, the direction is counterclockwise. That doesn't change. If it came up negative, it'd be clockwise. And then finally, I3, I take the junction rule. I1 plus I3 equals I2. That's my junction rule. I have I1 as 3 plus I3 equals 4. So I3 equals 1.
On the test, when you get asked a question like this, do you have to find I3?
Mm-hmm. Yeah.
Even though we don't need it for the side current through one of the resistors?
Right, yes, but yes. Mm-hmm.
Where do you get the negative on the outside of the vacuum?
This one right here, Catherine? Yeah, let me show you. I solved this equation. Let me write it out. I solved this equation up here. And so I can do it just a slightly different way. I have negative 2I1 equals negative 6 plus I2 minus 4. That might have been the way.
We just got 2I by itself, so.
Right, yeah. I just,
Yeah, I was just wondering where you got the negative 6 from, because they went 5, 6 minus 5.
right here, you mean? Right here? When I take this whole thing over to this side of the equation, it negates it. I subtract that from both sides.
You could have taken 2I and just made brought it over there and left everything else the same.
You could have, yeah. Mm-hmm. Okay.
So is the, how do you know which direction the current's going to fly through if you're just solving using junction rule?
Well, it came out positive, so I know that I did choose it correctly. All right. There is a current through that circuit. Yeah, there is a current I3. It's just there are no resistive elements there for us to touch. Yeah, there is a current. It's like if a tree falls in the forest and nobody's there to hear it, does the tree really make a sound? It makes a sound, right? Same here, sort of.
It's vibration. If it's positive, is it always going to be counterclockwise?
No, it's going to be whatever you chose it to be. So here, I3, we chose it to be clockwise, and so it's positive. I1 was 3 amps. You see I1, it chose to be counterclockwise, and it's positive, so it is counterclockwise. So here, in fact, it chose all the directions correctly, and so I just record them as I wrote them. But on the test, you have to record both the magnitude and the direction of the current. All right, you will have a test question. It'll be very similar to this. I mean, different numbers, and the resistors will be moved around, but it'll be laid out like this on a 2-loop circuit. Jose?
So, you say to the right on I2, but wouldn't that be the same thing as I1, just counterclockwise? Because it is making a rotation at the time.
I2?
Yeah.
No, I mean, I could describe I2 as counterclockwise or clockwise. I mean, I2 is...
No, I'm talking about... Yeah, that's what I'm saying. Because you put to the right...
I2 only travels from here to here. So it doesn't make sense to call something clockwise or counterclockwise moving in a straight line. I mean, it doesn't make a full loop. It just moves from here to here. I2 only exists right there.
But then again, we use the whole loop at the time for it.
No. No, I2 is only on this loop right here. I mean, only on this branch right here.
Someone use
For the upper loop, we use it though.
Because it's got
No, the current, but this, you went the direction, you went a certain direction, but you already defined your current to be for I2 to go that way. So,
Right.
whatever direction you chose to travel through your circuit, this is where I'm getting hung up with these positive and negative and stuff. First step is to define what your current is. And then once you do that, then you choose which direction that you're going to go through your loop. When you get to that bracket, that branch or spot, you're paying attention when you, well, like the resistor that's at 1 ohm, you've already defined your current, so whether it's positive or negative depends on the direction you're traveling versus the current that you previously defined.
Right, so whether this is positive or negative depends on 2 things. The direction of the current, like you said, as well as the direction that you're traveling. So here we were traveling in this direction with the current, and so it was -1 times I2.
Let's say I chose to go the other way, and this is where I'm getting hung up. Then I'd have got a positive I2,
Right.
but current can't be a negative number. So if I'd have laid it out how it came up with a negative number, I'd have known I've chosen the wrong way.
It doesn't matter, it does matter the direction that you choose for the current. You're right about that. So, well, let's say I chose this direction for I2, which we now know is the correct direction, but instead of traveling this way, you travel this way. You would still get a positive value for I2, because the only difference between this equation and this equation is a -1 on both sides, and that -1 just factors out. So, yeah. Don't worry, we're going to do some more problems. We're going to do another practice problem on this. And you know, if you look back at the old exams, you'll find this on every exam. If you go back a semester or two, you'll find the algebra gets more difficult, because, man, you give this problem to people and you'll get 50 different answers in a class of like 15 people. Or you get different answers. Like, nobody gets the answer right because they get bogged down in the algebra. And so I really look for these equations, that you get these equations correct, and that's the bulk of it. And then if your algebra is wrong, it's like, oh, it's kind of -3 or whatever. So, yeah, so this makes your algebra a lot easier. You don't actually have to substitute one equation to another. People get bogged down in that. All right, that's why, like, anytime you see a branch that doesn't have a resistor, it's the algebra is a lot easier.
Why didn't we do the big loop for this one, the previous one?
You could have done the big one. That would have been good.
It doesn't really matter. All right? It doesn't really matter which loop you choose.
Like you need two different ones, correct?
You need 3 independent equations, yeah. But 2 loops and 1 junction.
All right.
So that would mean that you could use the big loop to get the inside of the junction rule, right?
You could do that, but that's gonna be difficult.
No, I'm just saying, but we could.
Mm-hmm.
Okay.
It makes your algebra more difficult. But yeah, you can do that. You could do upper, lower, and big loop. Those are 3 independent equations for 3 unknowns. You can solve that.
If you have more resistors in these, that's the problem.
Yeah, that's the problem. Because you got more resistors. You got more I's with coefficients in front of them. And that just makes your algebra more difficult. You're chatty this morning.
We need to learn.
Chatting.
Yeah.
We don't like have to make our own decisions.
Chatting.
The rules, go to the left, go to the left.
The weather.
Let me show you a really cool way to solve this. I think we did this last semester. Have time for this? Yeah, I have a few minutes. I'm just going to get it set up. Rules? Oh, shoot, I didn't write the rules. Okay, you can solve this by Gaussian elimination. You remember we did this last semester? By matrix, yes. By using the matrices? You remember that? Did we do that last semester?
It was extra credit.
It was extra. It'll be extra credit again. So I'm going to show you. So you construct your matrix just by putting equations 1, 2, 3 in the coefficients. So equation 1 is negative 2 I1 minus 1 I2 minus 0 I3 equals negative 10. Is that correct? That is equation 1, right? Yeah, 10, negative 2 I1 minus 1 I2 minus 0 I3 equals negative 10. Yeah, that's equation 1. But notice I wrote it I1, I2, I3 in that order. And then I can write equation 2 as 0 I1 minus 1 I2 minus 0 I3 equals negative 4. All right, so that's my equation 2. And then my equation 3 is I1 minus 1 I2 plus I3 equals 0. So I've written those equations in this way, and I can express that as an augmented matrix, it's called. If you take linear algebra, you'll take linear algebra? Some of you do, right? Yeah, engineers have to take it. I think chemists can take it if you want to get a math minor, which is a super fun class. It is. It's like one of the best math classes I ever had.
Just have you have to take calculus 2 to be able to take it.
Huh?
Just have in mind you have to take calculus 2 to be able to take it.
But y'all take up through Calc 3 or differential equations, right? Yeah, so you might as well. It's a lot easier in differential equation. Differential equation is like black magic or something. I don't understand. Look at that. But so you can write this as an augmented matrix: negative 2, negative 1, 0, negative 10. Let's see, I could just make these positive zeros, right? 0, negative 1, 0, negative 4, 1, negative 1, 1, 0. This is an augmented matrix, it's called. And if I get it into the form of an identity matrix, then that augmentation part, that thing on the side, it's called augmented because it has that little thing on the side. If I get it in the form of an identity matrix looks like this: 1, 0, 0, 0, 1, 0, 0, 0, 1. 0, 0, 1. Then what you'll have over here will be I1, I2, and I3. The values for I1, I2, and I3. Because notice, this is like saying 1 times I1 plus 0 I2 plus 0 I3 equals this value, which would be I1. So the goal here is to get this matrix to look like this matrix, and then the numbers that are here will equal the values for I1, I2, and I3. Right. you can have rules when you're dealing with these matrices, and you can program this pretty easily. You can do it even in like an Excel or C or whatever. What's the programming language these days? It's not C anymore, is it? Something else like Java, C++. Yeah. So you can program this pretty easily to solve a huge matrix, like a million by million matrix, and that's really useful for solving systems of equations. Or you can go online too and find things that are pre-programmed for you.
That sounds like a lot of fun.
It is. It's kind of cool actually when it works. There are some rules that you can do. You can multiply a row by a constant. You can also replace a row with that row plus another row. On Friday, I'll show you what this means.
If we make this matrix, if we get the three equations, do this matrix, and then put it just plugged in our computers here or our calculators, solve the matrix, and just put the answer we can say solve by calculator.
No, I can't do that. You have to show the steps. Let's see. You can. What's the other rule?
You just put it in the matrix.
I guess that's it. Oh, and then you can switch rows. You can also switch rows. Sorry, I didn't write the actual rules down. All right, so like you can move row 2 and row 1. Don't worry about it. Listen, you can do this for extra credit. I don't know how many points, 3 or 4 or so on the exam. But if you don't know how to do it, you don't want to worry about it, then don't worry about it. But it's kind of cool. I'm sorry, Brittany, what?
You have to do it like with solving all the equations, and then you would have to do it this way.
Either way, I mean, if you just want to do it this way, you get the right answer and you get
No, just make it sure.
yeah, but if you don't want to do it this way, you don't have to. Here. Like you'll have the circuit problem, and then you can solve it this way for a few extra points. All right, guys, we're going to stop there. I know it's a couple minutes early, but I have to get to my kindergarten class.
I'll give you a lollipop. Do my two equations.